I welcome you all to this course on microscale transport process. Let me give you a brief introduction of what this microscale transport process, why this course is important to you. Firstly, this momentum, mass and energy transport in sub-millimeter size system or channel under a driving force, that comes under the purview of this course. The subject received significant attention over last decade due to miniaturization of sensors, biomedical implants, making of novel materials and structured catalyst. There are several other applications as well. These are some of them I could think of right now. There is one important application that primarily put this subject in a primarily added a lot of importance to this subject, which is known as lab on chip. That means entire biochemical laboratory on the surface of silicon or polymer chips. What that means is that think of say somebody doing a blood analysis. The way it is done is the blood is taken in a bottle and then it is kept in a pharmacy shop. Then some reagents are added to it and the analysis is done on that sample. So, the patient goes there, gives the blood and wait for a day, and after a day the results come that okay, this is the result. Now, if there could be a chip, maybe in a simpler way I can think of as say a credit card type object in which the reagents are already loaded and the blood sample is just added, a drop of blood sample is added inside the chip. And then this reagent gets mixed with the blood sample inside the chip itself, inside the credit card itself, inside the credit card like object itself, and then then it gets mixed, and finally it is left inside that chip at some place where the sample can be optically interrogated, means something similar to swiping of the card inside a scanner. So, if this instrument is sitting on doctor's table and the patient goes there, he can give the sample and immediately he can get the scan done and immediately he knows what the disease is. I mean this is a kind of paradigm shift that is possible in day to day analysis. This is just just an example, blood sample. It could be just an effluent coming out of a chemical process plant. Chemical process out of a chemical plant, some effluent stream is coming out and then that stream needs to be analyzed. So, you take that in a bottle and then send it to the laboratory. It takes some time. By that time there could be some changes taking place within the sample itself, you never know, and then it goes there and it goes all the way to the lab and then it would be analyzed. So, there instead of that, if you can have a scanner and a chip and you go to the field where the effluent sample is coming out and if you can get the scan done there, that nothing like it. So, that is kind of the idea behind putting this lab on chip, what is mentioned here in this slide. Entire entire chemical laboratory on the surface of silicon or polymer chips. Why people got enthusiastic about this idea is that it can leverage the techniques that are developed over years for silicon based microelectronics industry. If you can arrange transport of electrons so precisely inside a chip, so why not doing it for a laboratory analysis. So, that is so you can leverage the technology that is already there, people have been developing for microelectronics industry to accomplish the right design or right production technique for lab on chip. So, and there could be polymer based chips as well. Instead of silicon based, you can have this chip made of polymer, which is cheaper and easy to produce, because if it is a biodegradable polymer, it can be made on a use and throw away basis. So, these are some of the things which is driving these microscale processes or microscale elements. The major concern here is that major interest here is of course miniaturization of sensors, as I pointed out, biomedical implants, and making of novel materials and structured catalysts, and there are more interesting areas that are coming up. However, this lab on chip is one such example that I put here. So, when we get to this microscale transport process, I mean, you are already familiar with transport phenomena, you have already studied transport phenomena. The way it is different, this microscale transport process, the way it is different is that there are certain scaling laws which I need to visit first. The scaling law, I can put it like this: if you write surface forces divided by volume forces, by surface forces I mean surface tension gradients or shear forces, shear stresses, and volume forces are gravity, inertia. So, if you write this, you will find that this is proportional to, the numerator is proportional to L square, where L is the length scale, numerator is proportional to L square and the denominator is proportional to L cube. So, this is equal to basically L inverse 1. So, if L tends to 0, this implies that L inverse tends to infinity. So, what this means is that volume forces become unimportant as you reduce the length scale, however, surface forces become dominant. So, this is something which you have to keep in mind, that we are more keen about accounting the surface forces rather than the volume forces in this process. Another issue here in this in the microscale transport process is that fluid is not a perfectly continuous structure. Instead, it is composed of several molecules. You remember in fluid mechanics class, we have studied Lagrangian formulation and Eulerian formulation, right. So, when you go to a reduced, when you reduce your channel size, and I mean we are talking about L tending to 0, when you go to that level, whether the continuum hypothesis stands there or not, that needs to be visited. What continuum hypothesis in this regard, I mean let me put together. Here it is physical quantities such as mass, momentum and energy associated with small volume of fluid containing large number of molecules are taken as sum of corresponding quantities for the molecules in the volume. What that means is, you take a volume around which you would like to know what is the mass, what is the momentum and what is the energy associated with that volume. Okay. So, what you do is you sum up all the molecules and sum up the corresponding quantities for all the molecules and you call that the mass. That means, you sum up all the mass of the molecules and you call that a mass. I mean that is the idea of this continuum hypothesis. Now, if you plot something called measuring quantity, okay, suppose on y axis if you plot something called measuring quantity, and on the x axis if you plot volume of the probe. Okay. So, you are using a probe to find out what is the density, okay, or what is the pressure at a point. Okay. Now, the volume of the probe, if measuring quantity is plotted as function of the volume of the probe, you find a trend something like this. if you say if you are looking at an atomic force microscopy, if you look at atomic force microscopy and the volume of that probe, you will find that there would be large fluctuations due to molecular structure of fluid. You take a volume, you take a cube, say. Now, you can have the size of the cube, you can choose the size of the cube. If the size of the cube is the one side of the cube, cube is L cube, basically volume is length to the power 3. If that length L is less than 0.3 nanometer, you find that there would be some large fluctuations, because then what you would be doing is you would be measuring something where the molecules which are going in and coming out, they will be interfering to the observation. So, the measured quantity, the quantity that you measure, that would be affected because of the molecule coming into that cube and the molecule leaving that cube. Okay. However, if you increase the length scale, if you increase the length scale, you will find that this variation subsides. The measured quantity becomes constant. The measured quantity is not changing with the volume of the probe. You can, I mean, I can point out that when the side is, for a liquid cube of side 10 nanometer, that means a cube of one side 10 nanometer, that contains approximately 4 into 10 to the power 4 molecules, and it has about 0.5% fluctuation in numbers. Okay. So, if your probe volume is a cube of side 10 nanometer, you can expect 4 into 10 to the power 4 number of molecules sitting there inside, and the number of molecules should be joining them, a number of molecules should be leaving them. That number is basically, the fluctuation is basically restricted to 0.5%. For gas to have this same number of molecules and same level of fluctuation, you have to have 10 times the length. All right. So, that is a typical example I can give. Now, you will consider 10 nanometer side, I mean, if 0.5% fluctuation is acceptable, I mean, you do not probably care much about it. So, you can assume that whatever quantity I measured, that is just fine. But if it is, as I said, below 0.3 nanometer, you will have a very large fluctuation. So, you cannot, I mean, you will not be, that cannot be taken, that kind of measurement. I mean, that measurement can be, it would be interesting to study the other interactions, but if you want to take that as the average, take that as the representative quantity for that area, that would be a little difficult. However, when we go to the higher side of it, that means when it is more than 10 micrometer, you understand what a micrometer is, I take it, right? You understand what 1 micrometer is. So, if it is a 10 micrometer, that means you express that in millimeter. How much it would be? 0.01 millimeter. So, if it is above 10 micrometer, then I see that the measured quantity, it has a turn, it is increasing, but it is not increasing in it is not changing in a random manner, but it is increasing consistently. Do you have any idea what could be the reason for this increase? The reason here is that variations in physical properties due to external forces appear. Suppose there is a fluid flow taking place. So, pressure at one point has to be higher than the other point, right, because fluid will flow from higher pressure to lower pressure. So, these macroscopic changes, I mean, these variation in physical properties due to external forces, that will become significant. So, it has to go either up or down. I mean the parameter will change, or it can remain constant. I mean, if the system, if it is a static system, if the system decides that it should be constant, that will remain constant. But if there is a variation, that variation is due to external forces that you can take. It is not because of molecular interactions. So, these you can understand how the length scale, how they play out here, how the length scale play out here, and how these how the measuring you have to be careful with the measuring quantity when it comes to working with these scales. And ideally, if you are looking for a measurement of physical properties per volume, it should be in that this is referred as microscopic region, this is referred as mesoscopic, and this is referred as macroscopic. So, if you want to know some parameter per unit volume, you should be working in this region, right, because you want to capture whether it is increasing or decreasing with external forces. So, you do not want to play or want to work with this region. Your probe volume should not be there here, but this part would be just fine. If it is below this, then you will have molecular fluctuations. You would be probably this is a very important part, this microscopic part, if you can really gather this information. However, if you are treating it as an Eulerian fluid, then you should be working with mesoscopic region. Now, when it comes to the Eulerian formulation, there is a definition of field variable. There is a definition of a field variable. A field variable is defined as the average value of corresponding molecular quantity. Let us say, let us write this expression as if R T is equal to average of some molecular quantity where this R prime belongs to this set. So, here if R T is defined as average value of, so this is basically average value of corresponding molecular quantity if this F molecular quantity R prime T for all molecules contained in some liquid particle in some liquid volume of delta V positioned at R at time t. All right. So, what you are doing is you are picking up a volume which is at position R at time t, and that volume is basically delta V. Within this volume, the molecules that are there, within this liquid volume, the molecules that are there, you take them as F. So, that corresponding molecular property is F molecule R prime T, and that R prime belongs to, that position belongs to this element, this volume element. All right. So, if Mi and Vi, Mi and Vi, if they are mass and velocity of mass and velocity of molecule I, and if I belongs to delta V, then you can write, you can define density as 1 divided by delta V sum of I belongs to delta V Mi, and the other expression that you have is say velocity, as a function of r and t, that is given as 1 divided by rho r t delta v sum of I belongs to delta v m I v I. So, what is done here is that you have defined these field variables, one is density, another is velocity, and that is defined for all the molecules that are existing inside this volume element delta v. The velocity that we calculate here, the density part is fine, you just sum all the masses and then you divide it by the volume. But the velocity that we calculate here, this is a special kind of velocity. What is that? Right. This is not just average velocity. It is there is a weighting factor involved in this. You can I suggest you check the units to make sure that we have we put the right expression. Check, put the unit of density, put the unit of volume, and find out that we have written the right expression. So, this would be the field variable. Okay. Now, when it comes to measuring the velocity, I mean why we are treating it differently is that when it comes to measuring the velocity, this measurement cannot be done by a pitot tube or other type of apparatus, because we are operating at a scale which is too small. So, if we want to measure a velocity inside a channel where the length is so small, this has to be done by some other method. The common method which is there available in a sense, it comes at a very high price tag, is that measurement of velocity using microparticle image velocimetry. That is the name of that technique. The way this technique works is that microparticles with diameters of the order of 1 micron are suspended in the flow. Microparticles of diameter 1 micron, they are suspended to the flow. Now, there would be a CCD camera that records through an optical microscope the transmitted or reflected light. All right. So, there would be recording, 2 pictures will be recorded by sending 2 light pulses in quick succession of millisecond, which would be a millisecond apart. Okay. And then there would be use of a cross correlation function to determine average velocity at point r. How is it done? In a CCD camera, the positions are recorded as grayscale values. Now, if it is defined, say the time, the 2 light pulses, they are in quick succession. So, they are at time t1 and t2. So, at time t1 there is a pulse, light pulse, and at time t2 there is another pulse. The light intensities in each CCD camera, the corresponding light intensities in each CCD camera. So, light intensity is given as I1 r, and in this case the light intensity is given as I2 r. I1 r and I2 r, r is a particular position and the camera records the light intensity. So, I1 r is the light intensity at a particular position at time t1 and I2 r is the light intensity at time t2 for that same position. What you do next is you write a cross correlation function which is defined as R n delta r, which is equal to average of I1 r, I2 r plus delta r averaged over n. What is n? N is you can divide the CCD pixel array. You understand what a CCD pixel array is? There would be several pixels. So, you have an array of pixels. That array is divided into number of interrogation areas. Number of interrogation areas n. Okay. And within that interrogation area, so you have an array of pixels, within that you have identified one interrogation area, okay, and that particular interrogation, within that interrogation area you are finding out this I1 at a location r and I2 at a different location r plus delta r. All right. And this is averaged over all pixel coordinates in the given interrogation area n. And so, delta r here is defined as pixel displacement vector. Then you choose delta r n such that delta r n is that delta r which maximizes R n delta r. So, you are picking up an interrogation area and then you are calculating this cross correlation function, okay, and then you are finding out that delta r which maximizes this R n delta r, and then you define velocity v for that particular interrogation area as delta R n divided by T 2 minus T 1. So, over this time instance T 2 over this time interval T 2 minus T 1, you are finding out what would be the delta r, I mean how much this, where it the over what delta r the maximum change of intensity has taken place, and that you are relating to the velocity. So, this would be the way you will be measuring velocity at a point when it comes to channel of this length scale. All right. So, you can similarly, you will see that there is a shift of the way we think about conventional measurements. So, all of them will shift as you go to this length scale. This is I just give you one example how the velocity can be calculated inside a microchannel. And this entire these pictures are taken through an optical microscope, mind it. So, you can understand how this whole thing works. what I will do next is I will try to identify some of the application areas that these microscale processes, where the microscale processes will be useful. The number one, I mean, let me identify this lab on chip application, because if I read some review article on microscale processes, if I read this, if I read any review article on microscale processes, I find this lab on a chip is something which people find very promising. I mean, this has lot of promise, and there would be lot of thoughts put to it. So, there are applications which I identified here in this list. There are pharmaceutical applications, R&D in drug development, quality control and screening. In layman's term, what this is all about is a particular drug, when it suppose somebody identifies a molecule that this molecule can cure so and so disease, but from that point to having this in market under some trade name, that takes long time, lot of effort from scientists, because that drug has to be stable inside human body, because in human body itself is a chemical factory. There are a lot of chemicals floating around inside. So, this drug has to, the drug should not react in an unwanted manner with those chemicals. So, you have to first ensure what the reactions would be towards various chemicals, towards different conditions. So, this drug molecule has to come into contact with various other chemicals, and you have to see what would be the product. So, drug screening is a major application where drug has to, that particular molecule has to come in contact with several other chemicals, and you have to study the interaction. So, these processes, I mean, you can do it in a bottle, of course. However, if you do it in a bottle, there are issues like you need more chemicals. I mean, here the requirement of chemical is much smaller, and you can automate this whole process in a chip, but there it has to be done manually or through some robotic arm. So, you here the process can be it is this for pharmaceutical uses, for R&D in drug development, quality control and screening, this kind of lab on chip could be very useful. The second area of interest here is environmental, where water monitoring and pollution control is involved. There you would like to know the concentration of pollutants as it comes out, as it is generated. So, there I have already discussed this lab on chip would be useful. Then there could be some medical uses, allergen detection, toxicology, then implantable drug delivery system. This is a very important application. The drug delivery will be done, but it will be done in a tailored manner. It is not that all drug is added to the human body at a time. It has to be released when you want it to be, and at the rate you decide. Then flow meters in biomedical implants, how much of drug is released from where, or the biomedical implants are used there is huge amount of research going on in biomedical implants for various reasons. Then tailored medication, the drug would be released only when it is required, or when and how you want to, that you decide. It is not the nature does not decide, rather you control it. Then the life science, that has a lot of lab on chip has important application in that area as well. Diagnosis of disease, gene identification. Then industrial pollution control, bioreactors, food composition to check pesticides and antibiotic residue. Testing of food, there the lab on chip has important application, because again you need to analyze then and there at the point where the food is being used or food is being generated. There itself you want to use it, there itself you want to analyze it. You cannot afford to send this to a lab and wait for 2 days, because by that time the food will perish. The forensic medicine, that is also another or rather forensic applications, that probably the right one would be forensic applications, where the sample is too small and you want to know what that is all about. A blood stain is there and you want to know whose blood is that. So, there you cannot afford to have large volume of sample and you cannot treat it with a large volume of reagent. Here the sample size itself is very small. There are other important applications. One application is microreactor. Okay. Microreactor, there instead of having a packed bed catalyst where catalysts are arranged in a random manner, you can have a structure similar to honeycomb, okay, with the channel internal walls of the channel coated with a catalyst. There you have a very structured catalyst instead of a random one. You can have extraction chamber made of, I am talking about solvent extraction using these. Then heat exchanger in electronic circuits, that is another area. Micro droplet as templates, you need to generate micro droplets in various applications, and there these microfluidic devices are important. The advantages of lab on chip. The advantages are, number one, shorter time. If that has to be done manually, if the analysis has to be done manually, you have a reagent, somebody has to add it. Suppose 10 reagents are to be tested to find out what is the target, I mean the sample, you have to mix it with 10 reagents to find out with which reagent this sample is reacting, and from that you try to find out the characteristics of that sample. But mixing it manually, it will take long time, but if you have 10 such channels engraved inside the chip, that would be much easier. Second point is upfront capital investment reduced. If you do an analysis using a spectrophotometer, which is say which can scan over a wide range of wavelength, you have to invest that, you have to invest some money to purchase a spectrophotometer. But instead of that, if you can make some instrument which can scan only at one particular wavelength, so that way you do not have to your expenditure would be less. Of course, that instrument will not be useful at other wavelengths. However, if this instrument, you want to dedicate that instrument completely to the analysis of that particular sample, then it is fine. Then you are not going to use any other sample. So, you know this is the optimum, this is the wavelength setting. So, the instrument is meant for analysis of that particular sample. So, that way you can reduce the upfront capital investment. Suppose somebody wants to analyze water in a swimming pool. So, he need not have to make a complete lab next to the swimming pool, a very comprehensive, very detailed lab to analyze the water. He can have just a small scanner in which he can analyze the water sample. So, that is probably the idea people had in their mind when they are putting up these proposals, that yes, lab on a chip could be useful, etc. Now, the next point is close to real time measurements, blood, food and effluent samples. You can measure, as I said, you can measure the sample then and there wherever the sample is generated, instead of putting it in a bottle and waiting for another 12 hours to get to the lab and next to the right instrument. So, that advantage is there. Small requirement of samples and smaller chemical footprint. You use 10 chemicals to find out with which reagent, with which one the sample reacts in the way you thought, and then what will you do with those chemicals? You have to throw them on the, throw them out in the environment. So, here the chemical footprint would be much less in this, if such type of application is picked up. Then digital output and interfacing with software, that is possible, because you check the color. Okay, it is changing from red, this colorless to purple, and you have ways to measure that color. But instead of depending on human eyes, you can do the measurement in a digital manner. So, that is that is one of the objective of bringing this lab on chip. In drug discovery, small volume of expensive reagents, parallel operations, high throughput screening and reduced human error. So, in drug discovery, these added features that this lab on chip brings. So, these are some of the advantages people put together. I mean, if I pick up a book on microfluidic devices, I find that they say lab on chip is something which would be driving the microscale transport process research, and this is something people are looking forward to. Of course, it is not yet available in some places. For example, in drug discovery, people are already using few things there, and some companies are already there who are in fact in their website they show how what kind of lab on chip they built, the pictures, etc. But this is something which people expect out of a lab on chip, and that is why they are kind of getting interested into it. All this generally comes under the sensor and controlled release, and under the subject of sensors and controlled release. Okay, advantages continued. When we go for a microstructured catalyst, as I said, instead of having a randomly packed bed, you can have a monolith, something like a honeycomb with internal walls coated with a catalyst, that we call a structured catalyst. There you can have high surface to volume ratio, which means increased catalytic activity and better heat dissipation for highly exothermic reaction. If you load in one place, again you think of a probe volume. Okay, if you load your catalyst randomly in some places, suppose as the two streams enter into a packed bed, randomly packed bed of catalyst, as the two streams enter, it is encountering the catalyst on the way. In some volume, they find that the catalyst loading is much higher, and in some volume they are finding catalyst loading is much lower. So, accordingly the conversion also would be guided by the amount of catalyst it encounters. So, there could be, if too much of catalyst is there, then there could be extraneous reactions setting in, there could be thermal runaway, that means a lot of heat gets generated, and if extra heat gets generated and if it cannot be dissipated, if it cannot flow quickly, then there would be sintering taking place, the catalyst gets destroyed, and also if there is unwanted products generated, that will also result in poisoning of catalyst. So, you want reduced coking, thermal runaway, reduced thermal runaway, reduced sintering, and for these purpose, if you can have a structured catalyst, that means if you can have the channels that are if you have channels whose dimensions are all uniform everywhere. So, in that case this problem does not arise, and if you can create more surface area per unit volume in those channels, nothing like it. So, you can you give more catalytic activity induced in this. So, these are the advantages for which people are interested in getting into these microstructured reactors. Of course, I mean why they are not getting into this, I mean if so much of advantages are there, is of course the cost, because we are talking about borrowing techniques from microelectronics industry, and microelectronics industry that will not come very cheap, and people are used to having catalyst pellets and randomly packed beds, because those are cheaper. The other issue here is the robustness of the reactor. If you have a structured monolith, the reactor, you can expect the reactor to be more robust. You can have hazardous reactions at the point of use. Suppose some hazardous chemical is required for some use, you need not have to make that hazardous chemical and transport it all the way. You can generate that hazardous chemical at the point of use where you are going to use it actually. Difficult reaction that requires precise control and otherwise difficult reaction that requires precise control and otherwise not attainable. Please change this, otherwise it should be otherwise not attainable in a randomly packed bed. It should be not attainable. So, difficult reactions that require reaction that requires precise control and these reactions are otherwise not attainable in a randomly packed bed, such as making of propellant from carbon dioxide in a spaceship. So, this is some kind of reaction where you need very precise control. So, that kind of control is possible in a microstructured catalyst rather than in a randomly packed bed. Okay. There are other advantages as well, and of course, on the disadvantage, so nothing comes free. On the disadvantage side, of course, it is there. It is the cost. Here I briefly identify the components of lab on chip, the components that are there. I mean that these components need to be there, otherwise you cannot construct, otherwise you cannot accomplish the objectives that I mentioned just now. The components are, there has to be some pumping element, because reagent and the sample that has to be pumped inside the channel, inside the channels which are engraved on the chip. Then there has to be some valve arrangement, some fluid will flow when under certain condition and it will not flow if that condition is not met. So, these imposed flow, I mean you should be able to control the flow wherever location you want inside the chip. Then there has to be some separation modules. Okay. In conventional mass transfer, conventional chemical engineering operations, this is a major operation, separation. Okay. Separation, it can be separation of particulates from a liquid stream, it could be other type of separations as well. So, that has to be accomplished inside the chip. I will go into the details of these, but let me first point out what all other components are there. There has to be some mixing elements inside the chip. All right. There has to be some kind of mixing element. This mixing is done in a conventional chemical process, and if you are having sample and a reagent, then sample and reagent they have to mix. Then there could be heating. Heating is also another important issue. At some point the stream may be heated. So, that is also one issue. One major aspect here which you probably have not studied that much in a conventional operations is detection, because this whole purpose of this analysis is it is basically sensor, right, or a biomedical implant. So, detection is a major component. You have to detect because finally the objective is to detect the sample. You have collected some sample and you want to find out what pathogen is there. So, whether that water can be used or not. So, the pathogen has to be detected. So, there has to be some detection unit which probably you are not that much familiar with. So, these are some of the elements that we have, and in the next class what I will do is I will discuss one by one how these elements can be arranged in the how these elements can be arranged inside the chip. One thing you must remember here, that the flow is laminar and the interaction between layers are utilized in most of these components. You will have laminar flow, there will not be any turbulent flow inside the channel, and laminar flow means one layer is sliding against the other, and the diffusion between the layers, that you will try to utilize in many of these operations. With that, I stop here for today. In the next class, I will go over these elements in little bit more detail, and we will find out how we can implement these elements inside a chip.